Welcome to EH Classroom series. I am Daniyal Qureshi, and today, my dear friends, we are going to see the RLC circuits and the concept of resonance. What they typically tell you is that inductive reactance equal to capacitive reactance, XL equal to XC at resonance, or the resonant frequency is 1 upon twice pi root LC. But what the heck is it? And what does it actually mean? This video will explain everything you need to know about RLC circuits and the concept of resonance in a proper way. So make sure that you watch till the end, and now let's head towards our computer screen. And by the way, a quick message to the newcomers on this channel is that we have already completed 11 lectures so far in this Electros Classroom series. This is the 12th lecture. So if you really want to understand the core of electronics, you must go and watch the videos. I have covered them in as much simplicity as I can, that even a non-technical person can easily understand. Okay, so what is an RLC circuit? Now, RLC circuit is a very basic circuit containing R, that is resistance, L, that is inductance, and C, that is capacitance. If these three elements are connected, then that circuit is said to be an RLC circuit, and it can either be in series or parallel. Just to recall that in the last lecture, we saw the simulation of RC and RL network, okay, where only two elements were present, either resistance or inductance, okay, resistance or capacitance, okay. But here we are dealing with these three elements which are connected in a network. So it is highly advisable that you watch the previous video and then continue from here. Okay, so we have all these elements connected in series, which is actually energized by this alternating source of approximately 40 Hertz. Okay, and here are also sliders. We'll change them accordingly. And here are the scopes for AC source, resistance, inductance, and capacitance. Now let's start the circuit and see what happens. Okay, so now the circuit is active, you can see, and you'll observe the oscillations. Obviously, due to this AC source, these oscillations are produced. But now the waveforms will actually change due to these elements. Okay, so we'll see what are the changes. So currently these are the values set for the elements, that is 1 ohms and 140 millihenry and then 120.9 microfarads. Let's see the scope waveforms. Okay, first for the resistor, and again the phase difference between the current and voltage waveforms is same because this is the inherent property of resistor. And in the inductor, as the same we expect, you can see that the voltage waveform actually leads in an inductor, whereas the current lags. Okay, and in the capacitor, you can see that the current instead actually leads the voltage waveform. Okay, but now the question arises is what impact will be experienced by the AC source itself due to a combination of these elements like resistance, inductance, and capacitance. Okay, so here you can see the graph. Okay, here the voltage is actually leading the current waveform. Okay, even though we have a capacitor, still, okay, in capacitor you can see that the current is leading, but here overall in the circuit, the AC source is actually seeing that the voltage is leading. Okay, the current is actually lagging, and this is actually a sign of an inductive load. Okay, it actually means that the complete circuit is now more like an inductive load, because here the inductance is dominating, and that's why we are seeing a dominating effect of inductor on this circuit. Okay, and if we decrease this value of inductance, okay, if we decrease this value of inductance, definitely this effect will be mitigated, okay, or will be reduced to certain extent. Okay, so let's see what happens. Okay, so currently it is set to 140 millihenry. Now I'll reduce it, and you just noticed what change will there be in the circuit. Okay, so I'm gradually decreasing, so you'll see that the phase difference has now decreased. Okay, so now you can see that the phase difference is actually reduced by decreasing the inductance value. Okay, and now if we again increase the value, you can see that again the circuit will become more inductive, and the voltage waveform will actually lead the current, and you can see that it is actually surpassing the current. Okay, and the other thing which you notice, when I increase the value of inductance, this circuit current actually drops. Okay, you can see that if I increase this inductance value, the current will slow down, and this is because due to the large inductance effect, it will actually suppress the current more. Okay, it will actually resist the current more if the inductance value is high. On the other hand, if I decrease the value of inductance, you will see that the circuit current will increase again. Okay, because now you are decreasing the inductance value, so the current in the circuit must increase, because now the inductance effect will be much lower as compared to when the value was higher. Okay, now let's change the capacitance, but before that, let's keep the inductance to a minimum in order to avoid its effect in the circuit. Okay, so currently the capacitance is set to 140.9 microfarad. Okay, and if we increase the value of capacitance, you will see that while I increase the value of capacitance, you will see that the current in the circuit is increased. And why this is so? Because higher the capacitance, higher will be the charge and discharge current of the capacitor. Because in a capacitor, the current, the charging or discharging current is almost instantaneous. Okay. So if you increase the capacitance, a higher current will rush through and from the capacitor. While we decrease the capacitance, the circuit current will drop. Okay. As you can see, I have decreased the value, and you can see now the electrons are very much restricted. Okay. Because a very small capacitance value is there. So a very small charging or discharging current will flow. Notice other thing that now as the capacitor, now as we have increased the value of capacitance and decreased the inductance, you will see that the current is actually leading the voltage. Here you can see, okay, this yellow waveform is leading the green waveform, that is of the voltage. And this is because now here in the circuit, our capacitor is actually dominating. So all in all, these three elements, a combination of them actually decides what the AC source will experience, or what the AC source will see. And lastly, what about the resistance? Okay, what about this resistor value? Okay, currently it is set to very minimum negligible value of 1 ohm. But what if we increase its value? Okay, so let's see. We are increasing the value. Now you'll notice that at the AC source, both these waveforms are more or less in phase. Okay, they are actually in phase. Okay, the current waveform and voltage waveform are actually sitting on top of each other, having 0-degree phase difference. This is actually because now in the circuit, the resistor is dominating, or the resistance is actually dominating in the circuit. Okay, so therefore the weight of these elements will combinedly decide what effect will be produced on this AC source, or will be experienced by this AC source. Now let's reset our values, resistance back to 1 ohm. Okay, there is one more thing that I want to show you, is that notice while we change these values of inductor and capacitor, now at the AC source, the voltage and current waveforms are out of phase. Okay, they are not in phase. But notice while I change the value of capacitance, okay, around here, somewhere around 200 microfarads, you will see that the voltage and current waveforms are now actually in phase. Okay, how this is possible? Even if you have these two elements in series in the circuit, and we already know that the capacitor and inductor actually shift these waveforms, so why then we get a perfect match? Why this is so? So its explanation is very simple. So in this condition, the effect produced by the inductor is cancelled or nullified by the capacitor, or the effect produced by the capacitor. And what are the effects? They are actually their individual reactances. So here in this condition, the inductive reactance is equal to the capacitive reactance. They both are equal and opposite in this condition. And if they are opposite, then the overall effect in the circuit is actually nullified. So if the inductor shifts the voltage ahead by 90 degrees, so the capacitor will actually lag that voltage waveform again by 90 degrees, so that now the voltage and current waveforms are in phase. And this condition, my dear friends, is known as resonance. Okay, where the inductive reactance equates the capacitive reactance. One more thing that you might know is the capacitor and inductor are frequency dependent components. Okay, so what will happen if we increase or decrease the frequency? Definitely there will be some effect, and we'll see that effect. Okay, so first let's note the amount of current that is flowing through the circuit, which is approximately 3.9 amperes or closer to 4 amperes. Okay, now if I the current frequency is set to 40.5 hertz. Okay, and now if I increase the frequency, carefully observe, I have increased the frequency, you can see that the current has decreased. Okay, how much is the value? You can see that it is now closer to 1 ampere. Earlier it was 4 amperes, and now at 40 again, if I go at 40.5, so we'll again get the current of 4 amperes. And now let's decrease the frequency. So I am decreasing the frequency. Now notice, You have decreased the frequency and again the current has reduced. Okay. You can see it, you can check its value. It is actually closer to 1.5 or 1.3. It is actually decreasing because the circuit is yet to be stabilized. But now once it has done stabilization, you can see that it is 600 or 700 milliamperes. So why at a particular frequency the current in the circuit is maximum? That frequency was actually 40.5 hertz. Okay, and on the either sides of that particular frequency, if I decrease or increase the frequency, you get less current flowing through the circuit. Okay, why this is so? Because that frequency of 40.5 hertz, my dear friends, 40.5 hertz, again this frequency for 40.5 hertz is actually known as the resonant frequency of this LCR circuit, okay, or RLC circuit. At this resonant frequency, the circuit oscillates the most and provides the least resistance, provides the least impedance to the current. Okay, because there is not just a resistance, but there are also these reactive elements, okay, which will impart togetherly, they will actually impart what is known as impedance, okay, to this alternating current. So this is the magical thing about the resonance. Okay, so what it means? It actually means that for a particular value of this resistor, inductor and capacitor, there exists a frequency which is known as resonant frequency, and only at that particular resonant frequency, if you provide a signal, only then we'll get a maximum current swinging back and forth in the circuit. Okay, only then at that particular resonant frequency you will get the maximum signal flowing through the circuit. And if you go around the resonant frequency, if you increase or decrease the frequency, then definitely you will get a smaller current. Okay, now that you have understood the phenomena of resonance, but you might think that what is the reason behind the resonance phenomena? Okay, so let's see. It is very simple and very logical. Okay, so the three elements in the circuit which are affecting the flow of current are basically the resistance, capacitance and inductance. Okay, these three elements are affecting the flow of current. So there are only two elements which are frequency dependent, which is capacitor and inductor. Okay, so according to the frequency they will change, but the resistance will not change. Okay, resistance is basically frequency independent. Okay, so this curve has two parts. One is the decreasing curve and other is the increasing curve. Okay, so if you correctly remember this curve, okay, so this left hand side curve actually represents the variation of capacitive reactance with frequency. Okay, so it actually declines with the rise in frequency, if you correctly know, and this curve will actually extend further from here, okay, very closer to zero. And on the other hand, this curve on the right hand side is actually the variation of inductive reactance with frequency. So at higher frequencies the inductive reactance is very high, but at lower frequencies you can see that the inductive reactance actually decreases, and this will further go down touching the zero. So as our circuit contains a combination of these three elements, okay, they are actually combined in the circuit, so they will produce a combined effect. So consider the scenario where our capacitive reactance is greater than our inductive reactance. Okay, because we can measure the capacitive reactance and inductive reactance by their respective formulas. Okay, so let's imagine if the value of capacitive reactance is higher than that of inductive reactance, then definitely the capacitance effect will dominate, okay, or the capacitive reactance will dominate in the circuit, and that's why we'll get a curve more similar to that of the capacitive reactance variation with frequency. Okay, and whereas if our inductive reactance is greater than the capacitive reactance, we'll get a curve more like the inductive reactance curve. Okay, so overall what it creates is a curve having a dip at a particular frequency, that is the FR frequency, and this particular frequency where our effective impedance of the circuit is very least, okay, or very low, okay, or the circuit impedance is very low, that particular frequency is known as the resonance frequency, where a minimum opposition to the circuit current is offered. Okay, so hence the current in the circuit will be at its maximum at the resonance frequency. So at this particular point the effect produced by the capacitor is nullified by the inductor, and that's why at this particular point we can equate XL to XC, or the capacitive reactance equals to the inductive reactance at resonance. We also know that the capacitive reactance is opposite to the inductive reactance. So at resonance they both cancel each other, and the only component remaining in the circuit which imparts some resistance which imparts some impedance is actually none other than our only resistor. Okay, and from the condition of resonance, that is XL equal to XC, we can derive this formula of resonant frequency, where we can find out the resonant frequency or the natural frequency of oscillation of the circuit for a given values of inductors or capacitance. So for this particular circuit, resonance is the only condition where the least opposition is offered to the current. Okay, and otherwise at non-resonant conditions or at non-resonant frequencies, these elements will produce some reactance. Okay, either it will be inductive reactance, either it will be capacitive reactance. So it will be combined with the resistor or with the resistance to offer a more greater opposition to the current, and that's why at resonance it is the only condition where we'll get the maximum current flowing through the circuit. This chart indicates the variation of overall circuit impedance with the change in frequency. Okay, but what about the circuit current with the change in frequency? Okay, so let's see. Here you can see that the curve is something like a notch. Okay, where at a particular resonant frequency our current is maximum. That is exactly what we have seen. Okay, if our impedance at the resonant frequency is very least, then definitely the current will be highest at the resonant frequency. Okay, at that same point when XL equal to XC, and otherwise the current is much lesser, and you can see that it is actually in this fashion. So this kind of circuit which only accepts the current corresponding to the resonant frequency, or which only accepts the current having a frequency equal to the or somewhere equal to the resonant frequency, okay, or near the resonant frequency, this circuit is also known as an acceptor circuit. Why acceptor circuit? Because it only accepts the signals having frequency equal to or near the resonant frequency. This circuit in its most basic form was widely used in radio circuits. Now it is not used in this basic form, obviously it is now more complicated, but in the earlier days it was very much popular due to its simplicity. Okay, this circuit is also known as a tuned circuit and also an acceptor circuit, because this can reject all other frequencies. Okay, because the radio spectrum is so huge and you want to tune to a particular frequency in the radio headset. Okay, so you definitely have to only accept the resonant frequency or the frequency that you want to listen to. Okay, so you can simply select your components accordingly. You can vary these components, and accordingly you can change this maxima, okay, around this frequency to select a particular frequency that you want. But notice that this acceptor circuit is not perfect. Okay, you can see that even frequencies very near to the resonant frequencies are also accepted. Okay, the opposition provided to them is almost the same which is provided at the resonant frequency. So this particular circuit, okay, will also allow some additional frequencies, will actually allow some band of frequencies and not a single frequency. Okay, because this is a practical world, not ideal world. Okay, so from this we can introduce the concept of quality factor. Okay, so the sharpness or steepness of the resonance curve, if it is sharper, then the circuit will be a more better acceptor circuit. Okay, it will only accept a very minimum range of frequencies and not maximum. And if its steepness is less, okay, if its steepness is less, then it will accept a large band of frequencies. Okay, so this quality factor actually determines this steepness or the quality of acceptance or rejection. Okay, so higher the quality factor, narrower will be this frequency range of acceptance. Okay, and lower the quality factor, worse will be your frequency acceptance quality. Okay, so now let's see the parallel RLC circuit. Here instead of the elements connected in series, we have connected them in parallel. Okay, resistance, capacitance and inductance. Okay, and there is an additional resistor connected in series with these elements, and this is just to make the simulation happen, because in such simulators there must be some resistance. It can be negligible which is connected in series to the capacitor. Okay, it cannot be directly connected, and that's why we have connected a resistor. Okay, as stated earlier, the same principles apply here. Okay, if we vary the value of inductance, what you expect to see? Okay, so now it is currently at 6.5 millihenry. I'll increase it. Okay, so while I am increasing, you can see that the current through that branch has decreased. Okay, while the current through this branch is almost the same, but here the inductor is actually restricting the current flow because you are increasing the value of inductance. Again, okay, that is same. While if you decrease, the value of current will increase. Okay, the oscillation will again start. And if we increase the value of capacitance, what will happen? Okay, if you increase the value of capacitance, you can see that the majority of current is being bypassed by the capacitor. Okay, here you can see a majority of current actually flows through the capacitor because the charging and discharging currents are actually increased if you increase the value of capacitance, okay, or increase the value of capacitor. While if you decrease, then majority of current will only go through the inductor and the capacitor will act like an open circuit. What about this resistor? Okay, so definitely if its value is higher, it is actually acting as a shunt resistance. Okay, because it is actually shunting the source. Okay, so if its value is higher, a very less current will flow through this. Okay, because its resistance is very high, that's why a lower current will flow. So this will cause a more current to branch off here, or more current will be diverted to these elements. While if we decrease the value of resistance, okay, let's see, I am decreasing its value. So you can see that while I decrease, okay, so it is around, yes, so now it is 1 ohms. Okay, so majority of the current will actually shunt through this and a very minority current will be diverted to the circuit. So the resistor over here is not doing something fancy or not much, but the main elements are here, capacitor and inductor, which we'll see. And again, if we look at the waveforms, the capacitor is ideal and the inductor is ideal. That's why in the capacitor the current is leading the voltage waveform by 90 degrees, and in inductor the voltage is leading the current by 90 degrees. Now let's see the most important part, the effect of frequency variation on the overall circuit current. Okay, so currently the frequency is set to around 30 hertz. Okay, for this values of elements. Now let's see what happens if we increase or decrease the frequency or change the frequency. Okay, so we'll first note that a very small amount of current is flowing. Okay, so at this particular frequency of 30 hertz, you can see that around the peak is actually 450 or closer to 400 milliamperes. Okay, so I'll increase the frequency slowly. Okay, I'll increase the frequency. Okay, so now we are at around 90 hertz. Okay, and you can see that the circuit current has increased drastically. Okay, now it is oscillating back and forth very fastly. And other thing that you can notice that at higher frequencies the capacitor is actually conducting more than the inductor. And why this is so? Because at high frequencies capacitor actually the capacitive reactance decreases with the frequency. Okay, while the reverse is true for the inductor, and that's why it opposes the current more. Okay, so here the capacitor will act more like a shunting element at higher frequencies than the inductor. Okay, and the circuit current, okay, you can see what is its value. Okay, it is it is actually now increased to around 4 amperes. Okay, which is very huge. Okay, now again coming to the 30 hertz frequency, and now we decrease it beyond that. Okay, or below that. Now we are actually at 10 hertz. Okay, you'll see that the circuit current has now also increased, even though the frequency is now less than that. Again, our circuit current, its peak is 4.5 amperes. Okay, so why at this particular frequency of 30 hertz we are getting the minimum circuit current? Okay, at the frequency closer to the 30 hertz. Okay, at the 30 hertz we are only getting around 400 milliamperes or 500 milliamperes. Okay, why this is so? This frequency, my dear friends, is actually the resonant frequency. Again, the concept of resonance is true for the parallel RLC circuit. Okay, but here instead of maximum current we get minimum current at the resonance condition. Okay, and one other thing you can notice at the resonance is that you get the maximum oscillation in this LC loop. This loop is known as the LC tank circuit. Okay, the pure LC tank circuit where you have a capacitor and an inductor. Okay, which oscillate back and forth. Okay, so at resonance condition these elements will oscillate at their maximum, but on the other hand the main circuit current will not oscillate. Okay, it will oscillate but with very lower amplitude. Okay, so this condition is completely opposite to that in the series RLC network. But remember, one thing for sure is true for both of the networks is that here also the XL will be equal to the XC. Okay, here the maximum current we get only in the LC tank circuit. Okay, and there in the series, because the elements are connected in series, the overall current will definitely be same, and that's why we get a maximum current in the entire circuit. But here the LC tank circuit, only there will get maximum current, and that's why, you know, we'll get a lower current here. Okay, and now a very good question. You might ask that in the series RLC network, we saw that the voltage and current waveforms were in phase, but why they are not in phase in this parallel RLC circuit? Okay, this is actually a very good question, and even I was confused in the beginning, but now I know its answer. See, this phase difference is actually due to the arrangement of the circuit. Okay, that was a series RLC network. Okay, this is actually a parallel RLC network. The difference here is that, okay, the difference here is that the voltage across these elements are same, okay, because they are actually in parallel. The only thing which splits up is actually their current, okay. But in the series, a same current was flowing throughout the circuit, and hence the effect that was produced by one element was compensated by the other element in the same loop. Okay, so that's why we were getting voltage and current waveforms in phase. Okay, but here they are not in series, they are in parallel. That's why even though they are in resonance condition, but you will get some effective reactance. Okay, you will get some effective reactance at this branch. Okay, there you can see that there are two branches where the current splits up here. Okay, it will go here and it will go here. Okay, so at this branch there will definitely be some reactance. XL equal to XC is definitely true for this, but it will not, you know, cancel out completely the reactance. Okay, definitely there will be some reactance at this point, and that's why the reactance, either it be capacitive or inductive, will impart some phase difference in the overall circuit current. Okay, will impart some phase difference definitely. And here from this waveform you can see that the current is actually leading the voltage. Okay, so you can say here that the capacitive reactance is actually dominating, okay, or the capacitor is actually dominating, and that's why we get a phase difference in the overall circuit. This graph shows the variation of overall circuit impedance with the change in frequency. Okay, so here the curve is opposite to that of the series RLC. Okay, it is completely opposite. And why this is so? Because, you know, very simple, according to the respective curves of inductive and capacitive reactances, you know, at lower frequencies, if frequency is very low, the inductor will behave as a short circuit. So a very high current will definitely flow through the circuit. Okay, but if we increase the frequency, then the current will drop. Okay, will drop linearly. And in capacitor, opposite is true. So, you know, there is actually a sweet spot where the current in the circuit will be minimum. Okay, because either of the components, if we increase or decrease the frequency, their conductance actually increases. Okay, so that's why there is only a single point, okay, where these two curves intersect, where we get a maximum impedance which is offered to the current in the circuit. This is our current curve. You can see the variation of the overall circuit current with respect to the frequency. Okay, so this is again completely reverse and opposite to that of the series RLC. Okay, here at the resonant frequency, our circuit current, our overall or main circuit current is the least. Okay, and if you increase or decrease the frequency, you will get maximum current other than at the resonant frequency. So this again goes hand in hand with what we have observed so far. If at the resonant frequency we are getting the maximum opposition or maximum impedance in the circuit, then definitely the current has to be minimum at that resonance condition, and otherwise it will be much higher. So in this particular parallel RLC network, we can see that at resonant frequency, it is actually rejecting or attenuating the signal. Okay, so any signal which is closer to the resonant frequency, it will actually attenuate it or reject it, and hence this circuit is also known as a rejector circuit. Okay, completely opposite to that of the series RLC, which is also known as acceptor circuit. This is instead known as a rejector circuit. Okay, and again this rejector circuit is not ideal. You can see that it is rejecting a band of frequencies. Okay, if you consider it a range from here to here, so it is actually rejecting a band of frequencies rather than a single particular frequency. So again, higher the quality factor of the circuit, higher will be the rejection capability or higher will be the rejection quality of the circuit. Okay, so it will reject only a narrow band of frequencies and not a large band of frequencies. Okay, So overall we can say that these circuits, that is series RLC and parallel RLC, behave as filter circuits. Okay, they either accept or reject particular set of frequencies. And last, one most important thing to remember is that be it a series RLC or a parallel RLC, the frequency of oscillation is actually only determined by these two elements themselves. Okay, only capacitor and inductor. Okay, or this LC tank circuit. So the frequency formula will be same for both of these. Okay, f equal to, or the resonant frequency equal to 1 upon twice by root LC. Okay. And that's it for today, guys. Hope you enjoyed the lecture, and if you did, then please like, share and subscribe. We are closer to 1,000 subscribers. Comment down below if you have any questions, queries or any suggestion. Thanks for watching and see you there.